And this is a north pole, this is a south pole. So this particular dipole moment, it is there, this m bar, it is making an angle theta. What about the torque experienced by that? There's a uniform magnetic field. Who will produce a uniform magnetic field? Already we are discussed in electromagnetism. Okay, let's get into this one. So what about the torque? So if you look at the force here, Fn, and the south pole should experience force opposite to that. This will be, and this having a pole strength m naught. So what is the force Fn? Fn is equal to m naught into b. Will it set up any torque? Yes. So let this L be the length. 2L will be the magnetic length. Now, will there be any torque acting on this one? So torque should be equal to torque about midpoint. Will take it. Torque about 0.2. This should be equal to Fn L, angle between them, sine theta. Or both will put it like this. So this will be Fs. What is the angle? This should also be theta Fl sine theta. So Fs, so this is it. What is Fn? M naught BL. So 2L M naught. What can be 2L M naught? 2L M naught is what? Dipole moment. Magnetic length is 2L and M naught is the pole strength. So this will become MB sine theta. Theta and MB bar, you can see from the diagram. Like this, what happened? We'll get the torque acting on a bar magnet kept in a magnetic field. If the uniform magnetic field is a form, non-uniform, then what we should do? We should calculate the force acting. Can you hear me now clearly?
Yes, sir.
I'll repeat once again. There's a uniform magnetic field. Now also, voice breaking.
No, sir.
Okay, clear now. The uniform magnetic field is there. I'll kept a bar magnet. This one. So let the dipole moment of bar magnet make an angle theta with the horizontal, with the direction of field. The north pole experiences a force Fn, the south pole experiences a force Fs. Then a torque is set up, Fnl sine theta, and both the torques will be clockwise. Both the forces acting on the dipole, on the poles, north and south pole, they set up a clockwise torque. And because of this, the net torque will be clockwise. So, and so with this, what will happen? So what we get is like a 2 FNL sine theta. So now what is Fn? Fn equal to m naught b L sine theta. So solving this, I'll end up this one. So what is the torque acting on the bar magnet given by m bar cross b? So now this is a generalized formula. This formula is applicable only when B is uniform. B is non-uniform, you can't use formula. You should calculate force on individual north and south pole, then calculate the net torque. I'm making things clear. They can test you questions with like that also. Then what is the interaction potential G given by U is equal to minus m bar dot b bar, or this will become minus mb cos theta. What is M? Dipole magnetic dipole moment. B is a external field. B is what field? Not produced by magnetic field. B is a external field. This is an external field. So what is the basic idea? If a bar magnet kept in external field, it will experience a torque. That how much it will experience a torque, it all depends upon the this condition, angle between M bar and B bar. Okay, let's analyze some basic condition. So if there's a uniform magnetic field is there, So I do have here a bar magnet, and there's a magnetic field. What is the torque on it? Will be zero, no? First, what is the force on it? Net force is zero. Torque is also zero. And what is the potential G? Will be minimum. You slightly displace this and release. If you slightly displace and release, so will it execute any SHM? That's what my question is. This particular bar magnet is going to execute the SHM. So when I release this slightly, so there's a direction of M bar. There's a direction of M bar. How the torque will act? The torque, restoring torque should act from M bar cross B bar. So it will act about its center of mass. It will act here. So this will be the torque. And so since it's a bar magnet, it's like a rigid body. So it will have mass M, dimensions. So if you take the bar magnet, so it will, the geometric length L, this is B. So this will have mass. I'll put W because M not all are there. Let me write W. W is a mass here. If they're thin, then you can, usually we'll go for thin bar magnets. There's a with that one. So now what is the torque acting? Torque acting should be equal to mb sine theta. There's a small angular displacement I given, or will give all the things. Okay, fine. This will be, so this should be equal to mb sine theta. What is the torque? It should be equal to torque, that the torque should be equal to I naught alpha. And how it will act opposite to angular displacement given. Theta is given like this. How the torque is acting anti-clockwise. So this will be mb sine theta. Then what is I naught? Moment of inertia about an axis passing through. What is the moment of inertia of such a bar magnet? Will be W by L square plus B square. Capital L, I'll choose that one. If the thin bar magnet, even B will become negligible. Then it will become WL square by 2L only. So this should become alpha equal to minus MB by I naught theta. In fact, it's going to execute SHM. Then the time period is given by 2 pi I naught by MB. What is I naught? I naught will be W by 2L MB L square plus B square. So this is the expression for time period of a bar magnet, where it is suspended about an axis, passing through and perpendicular to, passing through its center and perpendicular to its plane. It's going to execute SHM. So shall we call this as a stable equilibrium position? So when the bar magnet will be in stable equilibrium position, when its M bar, when the dipole moment is directed along the external field, then it's said to be in a stable equilibrium position. So about in stable equilibrium, if you slightly displace and release, it's going to execute SHM. And what is the time period of oscillations given by this particular formula? Now, what is that B? B is an external field. B is an external field, that one, not this one. So this is what? And now, what happens if it is a bar magnet, if it is aligned in a position where M bar will be opposite to B bar? I'm making the bar magnet. Let it get aligned here now. So what is the first net force? Will be 0. Net torque 0. And what is potential energy? It is maximum. And this is an unstable equilibrium. So on what basis you can call this as unstable equilibrium? Let me slightly displace it. Small displacement. No, this is north. This is south. So you see the force. This force will be acting like this. And this force will be acting in the direction. And how is the displacement given? The displacement is given about 0.2. And how the resultant torque will act in this direction. So look at the angle theta in torque. This tau naught from where it has come? MB, what is the angle between M bar, MB sine of? Agree this? Why sine of 180 minus theta? Because M bar will be directed in this direction. No? M bar will be like this of the bar magnet. And B bar is in this direction. What is the angle between M bar and B bar? Sine of 180 minus theta. And this torque will act in clockwise. So look at the torque. Torque is set up in the direction of angular displacement. So shall I say this is a restoring torque or destabilizing torque? It's a destabilizing torque. Earlier what? It was a restoring torque. Depending upon situation, I'll call it restoring. What it will restore? It will restore its equilibrium position. So it will, if you disturb it, what will happen? It will never come back to again that position. Means it will again get aligned M bar in the direction of B bar. So this unstable equilibrium, we don't have anything. Now if similarly, it not oscillate about unstable equilibrium. About stable equilibrium, it will oscillate. Now if the bar magnet is aligned, if bar magnet is kept perpendicular to this one, how the, what is the equilibrium, nature of equilibrium? Can we say? Not equilibrium, no? What is the first torque? Non-zero. What about force? Force is 0. What about potential is 0? It's not in equilibrium. You should not say equilibrium. What do you mean equilibrium? Net torque, net force should be 0. Net force is 0, but net torque is non-zero. And potential is what? 0. So potential is 0 means not in equilibrium. Potential is minus MB, stable equilibrium. Potential is plus MB, unstable equilibrium. See, net torque, net force should be 0. There's a basic necessity for equilibrium. Net torque is non-zero here. So when it will be in equilibrium, when M bar parallel to B bar or anti-parallel to B bar, that's all. On net force, net torque should be 0. What I discussed, uniform. So they'll bring this bar magnet, they'll keep in the field of long wire. Due to long wire, how the field will be non-uniform. Just go back to the electrostatics. We have discussed several cases can be introduced here also. So what is the now conclusion? If a bar magnet kept in axial field, it's going to experience a torque or a force